the time domain representation of the signal appears in the upper right. In this representation, we see that the signal consists of areas of relatively stable electrical activity called of the sEMG signal that comes from the muscle that are interrupted by these large offsets. And these pulses, these offsets, are due to movement artifact. And we would like to remove them as best as possible and preserve the baseline and contraction. In order to remove these signals, we need to use movement artifact. We need to use a high-pass filter. And in order to select the cutoff frequency for the high-pass filter, I looked at the power spectrum density plot of the signal. Now, in this power spectrum density plot, we see that up to 20 hertz, approximately 20 hertz, there's a large signal component. And this is that same low frequency movement artifact that you see in the time domain in the upper right. And different spectra from different contractions were also compared, and in all cases, these low frequency components occurred below 20 hertz. So a 20 hertz cutoff frequency was chosen for this filter. As for the filter type, it was chosen to be a first order high-pass filter, and this was based on comparing step responses of different filters, and the step response that at least overshoot, and therefore would distort the signal at least, was chosen. Now, the other, and then on the upper right now we see the time domain representation of one of those movement artifacts that you see between contractions. This is just to show that the filter that was the high-pass filter produced a 43% reduction in the movement artifact. And the movement artifact can be further reduced with software filtering once the signal is required. Now, and now the other question that we need to address is the question of noise. So in order to analyze these signals, the performance index software compares the signal waveforms. So for that, we need to remove the noise component as best as possible. In order to remove the noise component, we need a low-pass filter. Now, although the bandwidth of the sEMG signal was from 0 to approximately 700 hertz, different levels of contraction. These acquired signals were recorded from our 12 electrode test sensor and then were digitized and stored in a data file. This data was acquired with our performance index software, and the signal to noise ratio of the acquired signals was calculated using the RMS parameter. The results from the FDI are shown in these two plots. On the left, we see a plot of the signal to noise ratio for all three spacings, electrode spacings, and for three different levels of contraction. And on the right, we see the score given by performance in their software for the same test condition. The first thing we notice is that the signal to noise ratio increases both as a function of electrode spacing and as a function of contraction level. However, the performance index score is in the 10 to 16 range for all the signals. Now, for most practical applications, we need a performance index of 4 to be able to analyze the data adequately. However, we see that our signals for the FDI are much larger than 4, and therefore all the spacings are adequate for provide adequate signals to be analyzed. Now, these results are much different than the results obtained from the vastus lateralis. So first thing to notice is that while the FDI has a high signal to noise ratio ranging from 7 to a high of 240, vastus lateralis has a signal to noise ratio that is a whole order of magnitude lower. And these low signal to noise ratio, this low signal to noise ratio results in correspondingly low correspondingly low performance index score for all the signals. And this is especially true for the smallest spacing for subject 1, and we see that the spacing is inadequate to provide performance index score of 4. And even at 80% level contraction, which is much higher than the level of muscle contraction that we use in day-to-day activities, which is 20%, the smallest spacing is only capable of providing a performance index score of 6, compared to the large performance index scores we saw in EPA. This, we're able to conclude that the smallest sensor spacing is not suitable for use in surface sensors. But more importantly, we're able to conclude that our system made the comparison, was able to discriminate between the ability of these 3 different configurations with 3 different spacings to provide adequate signals. So, in summary, I designed hardware that acquired data from 16 electrodes and was able to acquire low noise, low distortion, and high precision, and software which was able to select from multiple configurations of the sensor. And by doing this, I was able to compare different sensor configurations. And in a simple experiment to verify the abilities of my system, I was able to conclude that sensors should have an electrode spacing that is greater than 2.5 millimeters in order to provide a signal to noise ratio of 2. Now we know that a signal to noise ratio of 2 with some applications might be particularly good. However, the software is very sensitive and can identify motor activities and motor units in the signals successfully. And with my system, I was able to simplify the evaluation of the different sensor configurations because I was able to make the comparison of 3 different sensor configurations by acquiring signals from just one sensor. And the system that I developed will provide a useful tool to investigate sensor design in the future and will make it possible to acquire better surface electromyographic.